Okay, let's complete the life cycle of stars by having a look at the life cycle of much larger stars than the Sun. And by much larger, I mean something between 10 solar masses up to something like 40 solar masses. Now, there are stars that are much bigger than that, and there certainly were in the past, in the early universe, stars very, very much bigger than that. But they're quite exotic things. And so their life cycle may not bear a whole lot of resemblance to what I'm going to talk about here. I'm going to, these stars are pretty huge and pretty exotic, but those ones are pretty weird. So I'll leave that until you become a researcher in astrophysics and you can learn all about what those big stars do and come back and tell me about it. I was telling you the other day, wasn't I, about this, in the science news right at the moment, this giant variable blue star in a galaxy far, far away that's just suddenly disappeared, and they don't really know why. So yeah, they're bigger than 40 solar masses. They really are getting into weird stars. So the start is the same with a giant molecular cloud. You might remember that the last time I talked about giant molecular clouds, I was talking about the Horsehead Nebula, and I said that it had been the site of the picture that got everybody really excited when Hubble was sorted out. Turned out I had entirely the wrong nebula. Sorry about that. I should have been talking about the Eagle Nebula. This is the Eagle Nebula. This is that picture that caused all the excitement when Hubble first had its optics upgraded. This picture is known as the Pillars of Creation, and you can perhaps see why it looks like there are multiple stars glowing out from inside this giant molecular cloud. So if we get a core within our molecular cloud with a really high density of stuff around it, that core is going to grow very fast, and of course it then has a really high gravity compared to everything else around about it, and so it will start sucking things from around about, and so it'll get a lot larger than was the case for the cores that end up with our sun-sized stars from the previous talk. All of this, however, is the same. Falling in gas heats it up, blah, blah, blah. Eventually we get new hydrogen fusion, and as soon as we get hydrogen fusion, it becomes what we know as a main sequence star. And again, the basis of main sequence is the same. We take some protons, and we make helium, and we release a huge chunk of energy. However, we're now up here, and therefore we're talking about the CNO process, not the P2P chain. So we're into a much more efficient way of turning our 4 protons into a helium nucleus. And this is that more efficient way, or rather this is one of them. There's actually quite a lot of different versions of this, and stars quite possibly do all of them. But this is using the carbon that is manufactured in our star as a catalyst for manufacturing more helium. So if you follow it around with me, you can see the carbon gains a proton, becomes nitrogen. The nitrogen will then do beta plus decay to become carbon-13. The carbon-13 gains another proton to become nitrogen-14. The nitrogen-14 gains another proton, become oxygen-15. Oxygen-15 does beta plus decay to become nitrogen-15. Nitrogen-15 gains another proton, but instead of going back to being oxygen, it gains another proton and splits in two, firing out a helium nucleus and reconstituting our original carbon, which then goes round the cycle all over again. And it turns out that this is a far more efficient way of taking our 1, 2, 3, 4 hydrogen nuclei and turning them into a helium nucleus than the P2P process. And so stars that are hot and dense enough to do the CNO cycle will burn through their hydrogen vastly faster, even though they're vastly bigger. And so they may only last a few million years. Now, if you think about it, the sun, 10 billion years. These things may be 10 million years. So these things are 10 times more massive than the sun, up to 40 times more massive than the sun, and yet they chew through their hydrogen 1,000 times faster than the sun does before they've eaten all the hydrogen up, and they leave main sequence, which is amazing. Which just shows you the efficiency of this CNO cycle compared to the P2P process. The O, by the way, is of course it's oxygen that's made here as well as being made here, and then splits apart to create those two. Right. You don't have to know. You don't have to reproduce anything about the CNO cycle. You just have to know that the much bigger stars will burn through their hydrogen faster than smaller stars. Now, the next stage in its lifetime is the red supergiant. It's not very different from the red giant. The core contracts and the outside expands. Quite why it's the core contracting and the outside expanding is not immediately obvious. But that's the solutions for the mathematical models, as I said to you last time. And the solution for the mathematical models matches what we see in the night sky, so we believe it's true. Except, of course, these are a whole lot bigger, so these ones are supergiants. And we've talked lots of times now about the fact that the close red supergiant to us is Betelgeuse. And I say close, and what did we decide, 700 light years? So actually not very close at all. It's just super. So it's very big. And I've mentioned once or twice that Betelgeuse was the only star that Hubble could resolve. The only star that Hubble actually saw as a disk rather than a dot, because it's so enormous. So red supergiant. And our supergiants have a core of helium, because of course all the hydrogen has been converted into helium by this very efficient CNO cycle, and that contracts and heats up. The exterior envelope expands and cools, and then core fusion restarts with the helium fusing to carbon. So the helium mostly makes carbon, bit of oxygen mostly makes carbon within the core. And then once the helium is used up, it'll start carbon burning. And so having finished the helium stage, it then starts the carbon burning stage. And the carbon burning stage makes, as it says here, successively heavier elements manufactured in layers, with the heavier ones closer in. So, and that's what you've got over here in the diagram. We've got hydrogen outside, and then we've got carbon, then we've got oxygen, then we've got a silicon forming layer, and then the silicon is being infused to make iron right in the very center. And so we get these layers of successively heavier elements down to iron being formed right in the center of our red supergiant. And that forms a new equilibrium, which lasts for a while. Now, the fusing of carbon is perhaps a couple of million years. So it's not massively extended the life of this really big star. So fuses hydrogen for a couple of million years, and then once fuses carbon for a couple of million years, once all the helium has been turned into carbon, it then starts this process over here. And that process doesn't take very long at all. Now, what's going on here is given by this diagram. You're going to spend a lot of time with this diagram when you get onto nuclear. Normally we would be doing stars after we've done nuclear, and so this diagram would be completely familiar to you. So now instead I'm going to have to introduce it to you for the first time. So this is the energy binding a nucleon into its nucleus. So this is the energy that gets released when a nucleon is added to the nucleus. And then over here we've got the number of nucleons within that nucleus. And you can see over here, 0 of course would be just one proton, hydrogen. And then we get deuterium, and coming out here we've got helium-3. And you can see here why the P2P process was working. If you remember, the P2P process involved a couple of helium-3s merging in order to make just a single helium-4, and that doesn't seem reasonable. But then you look at the huge gap in energy involved in transferring between being helium-3 to being helium-4, and suddenly you see why it becomes worthwhile to bust apart two helium-3s just to make one helium-4, because there's this great big energy gain in the binding energy, because helium-4 is so stable. And then up here you can see why carbon and why oxygen are preferentially formed after the helium is gone, because they are little peaks in the binding energy diagram. So you know, carbon and oxygen over the nitrogen, because they peak up in the diagram. Now, of course, this is nucleon number, so you know, we might get isotopes of hydrogen, isotopes of nitrogen that are better in terms of their binding energy, and some isotopes that are worse, but roughly sort of nitrogen's in there between carbon and oxygen. And then you can see that we can carry on. As we carry on adding more stuff in, we talked about binding these things up to make silicon, and then silicon burning in the very core to make iron. Well, we can see the problem there is that the peak is at iron. If we try to do fusion any higher than iron, we start to go back down again. We start to lose binding energy. That trying to add things in to make heavier elements than iron is exothermic. Trying to add protons in, neutrons in to make elements up to iron. That one's the exothermic one. Loads and loads of energy being released. But as soon as we get to iron, to get any higher up this table, we've got to put energy in. We don't get energy out. So iron represents the finish. This process is called nucleosynthesis, making nuclei within a star. And when we get iron within a star, nucleosynthesis is done. Because the point of nucleosynthesis in a star is to release a whole lot of energy that makes the star run. Well, once we get beyond iron, where it's sucking up energy, it's not releasing energy. It's not going to spontaneously happen. You could see that if I took a uranium and I split it apart, I would make a binding energy gain, and that's why nuclear fission works. But we're interested in fusion. Fusion peaks out at iron, and the star can't get any further than iron. Now, I found this surprising. I mean, I only read it on Wikipedia, so I'm not 100% certain on it, but wow. This process of taking the carbon and pushing the carbon up to the iron might only take 1,000 years before it is no longer a reasonable thing for the star to be doing. And perhaps, you know, not so much that it's used all the carbon as just, you know, the conditions necessary to get a much smaller amount of energy out, therefore become quite specific. And so it's not that long before the star no longer has the right mix of elements, the right temperatures, the right densities to be able to achieve this small energy gain in going from the carbon to the iron. So this is quite a short chunk of the star's lifetime, the burning of carbon all the way up to iron. Once that's over, we get what's called a type 2 supernova. And there's lots of different ways that a type 2 supernova can happen, and each one has a very slightly different spectrum and a slightly different light curve, but they're all classed together as type 2 supernovas, which is core collapse. Sorry, needed a cup of coffee. Eventually, this fusing of the silicon to make iron means that we have this core that's stuffed with iron, and the iron won't fuse any further. We've just discussed it, iron won't fuse any further. So we get this incredibly heavy core starting to form in the center of our supernova, poisoning any other fusion. Because the iron's taking up all the space, the rest of the fusion can't happen because, you know, the silicon ain't going to bump into a silicon, it's going to bump into another iron. That's not going to fuse because we don't get any energy out for it. And so we end up with a core, a very center of our star, that's saturated with iron. And a point is reached, and it's sort of in an instant we go to core collapse. A point is reached where the weight of the iron core exceeds the pressures that might be holding it up, specifically the electron degeneracy pressure again. There's a huge electron degeneracy pressure in all that iron, in the same way there was an electron degeneracy pressure in the helium of a white dwarf. But of course, iron's a whole lot heavier, and this is a whole lot bigger star. So we get to the point where electron degeneracy pressure will no longer hold up the core, and the core collapses in no time. The collapse can reach speeds of over 20% of the speed of light. So, you know, the core's gone. We had a big stable star with an interior core, and then a fraction of a second later, we've got the remains of a star, and the core is crunched up away to nothing. the rest of it probably is going to carry on for a while, not even having noticed that the core is suddenly gone. Because, of course, the mass of the core is still there, so the gravity from the core is the same. But everything else, of course, has changed. As the core collapses, the electrons are forced in on the protons, and we get a weak force, a weak interaction taking place. We know what happens when electrons are forced in on protons, or when protons are grabbing hold of electrons. They make neutrons, and they release electron neutrinos. It's electron capture. We've done diagrams for that in the particles part of the course. But you've got to imagine here, this is the entire core of an enormous star. Every single proton, or just about every single proton, is being turned into a neutron. The numbers are mind-boggling. The numbers of electron neutrinos that get produced in a tiny fraction of a second are utterly, utterly mind-boggling. And those electron neutrinos all released out through the envelope of the rest of the star. Now, it's not absolutely clear how our core imploding inwards ends up being a supernova explosion outwards for the rest of the star. But it's probably these huge quantities of neutrinos. Now, neutrinos don't strongly interact with matter, but they do interact with matter a bit. And there's so many of them that even if they interact with matter a little bit, they're still going to transfer a huge amount of outward energy to the rest of the star. And the rest of the star tears itself to pieces in a supernova. And of course, we said on that curve earlier on that to get beyond iron, we need to supply energy. It's endothermic. Well, how better to supply energy to nuclear synthesis than a star blowing up? That's supplying a whole lot of energy. And so nuclear synthesis restarts, and all of the elements above iron are made in the supernova. And the person that realised that this was what was going on, this is how elements got made, was a British astrophysicist called Fred Hoyle. So Fred Hoyle, he had been working. He was working sort of with the Americans just after the Second World War. He realised that there were Americans who were working on sort of pumping huge amounts of energy into accelerators and trying to stick stuff together to make heavier elements. And then there were other ones who were studying supernovas, and it occurred to him that you could put those two ideas together. And so he worked all of this nuclear synthesis stuff out. He then went on to hold some quite crazy theories. He absolutely opposed the Big Bang as being the way the universe started, and write science fiction books. And then as a kid, I read a few of his science fiction books, actually. I think they'd seem very out of date if you tried reading them now. So, what's our outcome? What happens to the core? Well, one possibility of what happens to this collapsed core is that it becomes a neutron star. And that's for stars with masses between 10 and 25 solar masses. You remember this is the symbol for solar mass. So stars with masses between 10 and 25 solar masses, the core will become a neutron star. That is, that all those neutrons that get formed when all those electrons got formed on, pushed in all those protons, are of course fermions. And fermions will resist being pushed into the same state. And so our neutrons vibrate at high speeds, getting close to the speed of light, to try and avoid being pushed in on one another and try and ending up on the same state. It's the Pauli exclusion principle at work. But of course, a neutron is 2,000 times heavier than an electron. So where we said earlier on, electron degeneracy pressure couldn't hold the core up, neutron degeneracy pressure can hold the core up. So neutron degeneracy pressure arrests the implosion of the star, and we get this thing called a neutron star that's left behind. Now, the neutron stars, most of the mass is in the envelope. So most of the mass is this stuff that's getting fired outwards. The mass that's left behind in the neutron star isn't that enormous, because the electron degeneracy pressure can't hold up something that enormous. And so maybe only 2 solar masses left behind in the core. But you've got to understand that this is something with the mass of 2 suns and a density matching that of an atom's nucleus. Wow, what an extraordinary object. You hear all sorts of weird stuff bandied around about them, and I've never done the maths to check whether any of it is true. But I remember an astronomer saying once at a talk I was at that 1 teaspoon of neutron star stuff would have the same mass as everything in Wales. I don't know why everybody always picks on Wales. Have the same mass as everything in Wales. Not just the sheep and the grass and the people, the mountains, everything in Wales would have the same mass as a teaspoon worth of stuff of a neutron star. The other one I've heard it is that a teaspoon worth of stuff of a neutron star would have the same mass as the entire human population of the Earth. So imagine 7 billion people on one side of the scales and 1 teaspoonful of neutron star stuff on the other side of the scales, and that being in balance. Madness. Really, really extreme objects. The star was almost certainly rotating. The exterior of our sun rotates in something like 20 days. So the star was almost certainly rotating. Now, of course, when that interior crunches down and collapses down, we've massively reduced the moment of inertia, but we've got to conserve the angular momentum. So the only way to do that is if the angular velocity goes through the roof. And so they're rotating incredibly fast. They're also, of course, going to be hot because that GPE has been lost by the inward movement. So we've got these things that are at a uniform temperature of something like 50,000 degrees C that are rotating at massive speeds. And not every proton will become a neutron. That means that as they're rotating, they've got charge in motion, and that charge in motion, of course, means a magnetic field. But I'm not quite sure why this is true, but sometimes their magnetic field, or quite often actually their magnetic field, the poles of the magnetic field don't align with the axis of rotation. And the end result of that is that as the magnetic field is being swept around, it produces radio waves that sweep out across the galaxy like the beams of a lighthouse. And stars that do that are called pulsars. Because if you aim a radio telescope at one, what you get is pulses of radio waves as that beam sweeps across your telescope, and then it sweeps away, and then a fraction of a second later it sweeps back again. And so they're called pulsars. Now, the story of the discovery of pulsars is a sort of cause célèbre in science. Because they were discovered by a graduate student, by a PhD student called Jocelyn Bell. She found this regular pulsing with the world's first big radio telescope, which is Jodrell Bank, which is still operational outside Manchester. And sometimes if you drive in the motorways around Manchester, this great big thing looms up on the hillside above you, and that's the first really big radio telescope. She was working there. She discovered this pulsing, and she took it to her supervisor, and her supervisor said, "Don't be daft. It's going to be something man-made. Nothing in the universe is going to be pulsing regularly like that. It's going to be something man-made. Go away and find out what man-made thing it is so that we can eliminate it from our results." And she'd come back and go, no, it's definitely not man-made. It's definitely out in space. And he'd go, no, don't be silly, go away again, and try to convince her that she hadn't got a proper result. In the end, they all agreed that she had got a proper result and that it should be published. He gets first listing on the academic authors, which is, he was her supervisor, so that's fair enough. She gets second listing on the academic authors, and then other guys who worked on the telescope got later listings. Anyway, pulsars are taken to be real things eventually. It takes a little while. Well, that first one, because they were these regular pulses, they wondered if they'd found alien civilization. They jokingly called this first one LGM-1, Little Green Men 1. They wondered if they were finding the radio signals from another civilization, from the aliens. But once they'd found a few of the things out in the night sky, they realised they weren't aliens. They were some natural phenomena, and they set about explaining it, and hence we have neutron stars. And eventually, for work on radio telescopes, and specifically for finding pulsars, Jocelyn Bell's supervisor, the man who hadn't believed her, gets the Nobel Prize. She gets nothing. So, as I say, a cause célèbre. She was on the radio a couple of years ago. I was listening to her. She's an incredibly impressive woman. And she was saying that Yeah, actually, it was a really good thing um, because everybody knew she didn't get the Nobel Prize and everybody suspected she deserved it. Um, she she got every other prize going. So she was chairman of the Institute of Physics, and she was this and that, and she was, the reason she was on the radio 2 years ago is she got this $3 million prize for having discovered pulsars, 50 years after it had happened. Um, and like I say, she's a very impressive woman. She donated all of that 3 million to helping refugees, women, people from ethnic minorities to become researchers in physics. And she asked the Institute of Physics to manage it. So there's now a bursary, a fund in her name that helps other people maybe not have their supervisor disbelieve them and then take the Nobel Prize for their discovery. Now, just quickly, this one, nothing to do with the course really, but supernovas are numbered by the year they took place. So you might spot that's 1054. That's what 12 years before William the Conqueror conquered England for Jersey, and so this is the supernova that created this thing. This thing is known as the Crab Nebula, and so the Crab Nebula is the remains of the envelope that got thrown outwards by the supernova 1,000 years ago. That is what that's a picture of, and it's being lit up by the energy of the neutron star inside it. The neutron star inside it being a great big pulsar. Which is beaming X-rays and radio waves, and so we've got this great big pulsar trapped inside the remains of the envelope that it threw off when it supernovaed, pulsing away. And we know this supernova that created this happened in 1054 because Chinese astronomers wrote it down. They talked about the guest star that turned up in not only the night skies but was actually bright enough to be visible in the day skies when this supernova went off. So that's supernova 1054. No such writing in Western guys. Western guys were all worried about what William the Conqueror was going to do to England and that sort of stuff. They weren't interested in looking at the skies and writing any of this stuff down. They did notice a comet and sew it into the Bayeux Tapestry, but clearly weren't paying a whole lot of attention, unlike the Chinese. Now, there is another alternative to the neutron star. I said earlier on we were talking about stars between 10 and 40 times the mass of the Sun. So between 10 and 25, likely to make a neutron star. When we go bigger than that, they go to black hole after the supernova. Even bigger can go to black hole and supernova without having gone through the red giant stage. But I said bigger stars are quite exotic, so they're not the aim of this particular talk. We're talking about this kind of size of star that goes through the red supergiant or the red hypergiant, and they're sometimes known, the very biggest ones, to black hole via a supernova. And here, the neutron degeneracy pressure is not enough to stop the collapsing core. And so nothing is enough to stop the collapsing core. The collapsing core just keeps on collapsing. It keeps on collapsing for an infinite amount of time because it becomes infinitely small. And we call such thing a singularity. So something that is infinitely small, has no physical dimensions, but still has a physical value, is called a singularity. So here we have something that's become infinitely small, has no physical dimensions, and yet still has a physical mass. We can still measure its gravity, it still has gravitational effects, and so that's known as a singularity. Singularities are interesting things in mathematics because the mathematics tends to break down at the singularity. We get all of the mass of the core of this star being crunched down infinitely small, and our maths for what's going on starting to break down because we've got something that's infinitely small, which leaves open to speculation as to what exactly is going on inside the black hole and around the singularity. But part of the reason why it's speculation is even if we could see a black hole, and we are just, this last few years starting to be able to detect the existence of black holes. I can't really see the black hole itself, but we can see the action of matter falling in on the black hole. Even then, even if we could see to the black hole, the singularity would be hidden behind what's called the event horizon. It's a great word, event horizon, isn't it? And used as a name of a really nasty sci-fi film, a really horror sort of sci-fi film. So if you want to scare yourself in the middle of the night, watch Event Horizon. But the event horizon is the spherical surface some distance away from the singularity at which the escape velocity of the black hole is equal to the speed of light. Now again, we haven't done gravity. Normally we would have done gravitational fields before we got to stars. This time, because of the lockdown, we're doing things out of order. We haven't defined escape velocity yet. We will define escape velocity later on. Basically, it's how far would something have to go in order to be able to escape from the body it's on. So, the escape velocity at the surface of the Earth is something like 40,000 meters per second or something. I can't remember. We'll do the maths. Fire it at that speed and it will leave the Earth and it won't come back. So what speed would something have to be going at if it was close to a black hole to not be pulled back into the black hole eventually? And the point where that goes from being more than the speed of light, i.e. nothing has a chance of getting away from the black hole because you can't go more than the speed of light, to less than the speed of light, the surface at which that transition occurs is called the event horizon. Below the event horizon, nothing gets away from the black hole, including light. Above the event horizon, the gravitational field has sort of spread out a little bit, and light now has a chance of being able to escape from the black hole. Everything else is probably still going to get pulled in, but light has no chance of being able to escape from the black hole at the event horizon. And that, I'm afraid, is a definition you just have to learn. And there's a pretty simple equation called the Schwarzschild radius that defines the event horizon. So sometimes you're asked to work out what would the event horizon be for a star of this size, of this mass, if it all became a black hole, and you just bung mass into that formula. That's c, speed of light, and that's Newton's gravitational constant, a universal gravitational constant there. So you just bung the numbers in and see what the event horizon turns out to be. If I remember rightly, for the Earth, it's a kilometre or something like that, 10 kilometres. So if the Earth crunched down to a black hole, it's not going to, but if it could, what would be the event horizon? That's the kind of mass that you end up doing. Schwarzschild radius means something to me because when I was working on anti-gravity for British Aerospace, they paid for the mad Russian whose work we were trying to reproduce to come over and talk to us. And he was having long chats with me about how superconductivity worked and how to make the best superconductors and how that related to anti-gravity. And at one point he talked about the fact that we were talking about the superconductor Schwarzschild radius. And I was ever so impressed because I didn't know what the hell Schwarzschild radius was until I thought he was speaking sensible things. But me being me, I went away and looked up what a Schwarzschild radius was. And I discovered that actually he was not talking sensible things at all. A superconductor is not going to have a Schwarzschild radius. And that was the point where I started maybe to disbelieve him and think that I was on a fool's errand. Sorry, talking about me. Summary. So what of all of that do you need to know? Once again, reassuringly very little. I hope you were interested, but don't have to take a massive amount away. Big mass stars spend less time in main sequence. The red giant stage can do nuclear synthesis. That word you do have to know. Nuclear synthesis all the way up to iron. You'll do a lot more on the binding energy curve that we talked about, and iron being the peak of it, later on in the course. Supernovas then perform nuclear synthesis for everything else. Now, I hope you're thinking that's extraordinary. Copper's heavier than iron. So all the copper we use, think of huge quantities of copper that modern society uses. All the pipes around your house, all the wires throughout the world, all made out of copper. All that copper was made in supernovas. That doesn't blow your mind. Why are you doing physics? Go and do media studies or something. I mean, that's just extraordinary. All of the copper in the world was formed when stars that predate the sun blew up. Wow. Anyway, after our supernova, after our type 2 core collapse supernova, then we might get a neutron star, or we might get a black hole. And I think that's probably about it. Right, there you go. Last thing, I said you have to memorize this definition of what an event horizon is, because occasionally they ask in the exam. And I'm pretty sure that'll be it for this one. Hope you enjoyed it. I think the next one is still going to be about supernovas and black holes, but a bit more technical stuff about supernovas and black holes, stuff that is actually properly on the course, rather than this, which is, important background knowledge, but not necessarily anything that's going to get examined very much, apart from the half a dozen statements that are written down here. Okay, bye.